So this is the FP1 exam from 2024. The first mark is the easiest mark in all of A-level maths or further maths. You just have to put the number 3 into here and type in a log of 3 plus 3 squared, which is this number here. And now you don't get given Simpson's formula in the formula book. Just have this in your head: a third times height into ends plus 4 times odds plus 2 times evens. Because the heights, by the way, just means the distance between the two things. So in this case, a half. And then what I mean by these is the ends is this number and this number, so you add those together. The odds are the first term's number, the third term's number, and the fifth term's number in this case, and the evens are the second and the fourth. You don't count these as terms, right? This is the first term, the third, and the fifth. This is the second and the fourth. These are the ends, and they're the ends for a different thing. They're their own thing, right? So the first is here, the third is here, the fifth is there, and then the second and the fourth are there. And just put those into the formula there, and you end up with this number here. And the final mark, of course, this root can just go at the top as a power of half. The half brings down. It doesn't need to be in the integral, so it comes out, and then you just halve this number, and you get this here for your answer. And that's all of that done. This question here, now, the mod can do one of two things. It can either do nothing. If the input here is positive, so if this thing here is bigger than 0, this mod doesn't do anything. And to find the critical values of this, I just said x squared minus 2x equals to x. I guess we can say, well, that happens when x is less than or equal to 0 and bigger or equal to 2, because the critical values of this are 0 and 2, I guess, if you factorize this. And it's a quadratic right up, so you have to be to the left of 0 or to the right of 2. And if we solve this, we get the answers of 0 or 3. And both of those are within this range. So both of those are actual answers to this. So these two things do actually meet at 0 and 3. The other thing the mod can do, if this inside input is negative, I should have really put a strict sign here, but it doesn't actually end up mattering. But if this thing is negative, then you times this by minus 1. I mean, I guess if it is 0, you also times it by minus 1. It just doesn't do anything. So this is technically correct, I think. But if it's less than 0, the mod times the whole thing by minus 1, and then we look for the intersections. Now, likewise, because that must be the opposite to this is true here. And then, of course, you can solve this, and you get these two answers, which are also both in this range. So therefore, these are all intersections of this actual or critical values of this thing here. Now, how do we know whereabouts we are in these? Well, you could draw the graph to find out. So this is the graph of x, and then the graph of x squared minus 2x looks like that, has roots at 0 and 2 as already discussed, but it's the mod graph. So any negative area needs to be flipped over and put at the top like this. And now we can just see, well, here's the intersection at 0. Technically, this one is less than or equal to this one at 0, right? Because they're equal to each other. So x equals 0 is the solution. And it's also less than the line between here and this intersection up here, which must be the intersection at 1 here and the intersection at 3 over here. So it must be between 1 and 3 and at 0, and that'll be our answer. The L'Hopital's rule question comes next. So firstly, we need to maybe just combine those two things together and verify that as you go to 0, the limit of the top one is 0, and the limit of the bottom one is also 0. Therefore, we can apply the hospital because we get a limit going to 0 over 0. So we're allowed to apply the hospital, which means that we just need to differentiate this one and differentiate this one separately. And that if we take the same limit, then those two limits are the same. So differentiate this to get, of course, 1 minus cos x, and differentiate this with product rule to get, differentiate that one, it just goes away, leave that alone. Leave that alone, differentiate that one, and we get this here. And now we can shove in 0, 0 again. Except when you do that, when you shove in 0, 0, you're going to get, again, 1 minus cos of 0 is 1 minus 1, which is 0. And on the bottom here, of course, this is 0, and this is 0, which is 0 plus 0, which is 0. But that's okay, because we're still, therefore, getting a limit that says 0 over 0, which means we can just apply the hospital again. Like, imagine if you just got given this question to do, and you evaluated it, and it gave you 0 over 0. You'd be like, oh, well, I'm just going to do the hospital. So just because we're here having done it once doesn't make a difference, right? We're just going to do it again. So we differentiate. Of course, this differentiates just to sine x, and this differentiates, again, using a bit of product and a bit of non-product. But now, finally, as we go to 0, sine x just goes to 0. So we get 0 over, in this case, 2, which is just 0. And so we have the answer of 0 here in this question here. The Taylor series is given by this. Therefore, we have y equals f of x is this. Given pi over 4, comma 1 is a stationary point. Now, stationary point means dy by dx equals 0. So what we can do is we can throw x equals this, y equals this, and dy by dx equals this all into here. And that ends up being quite good because the middle term, of course, goes away. We can times everything by root 2, and we'll get d2y by dx squared is minus 1, which is negative. It's less than 0, so therefore it's a maximum. show that d3y is this thing here. Well, what we can do now is we can differentiate all of this, I guess. We need to do a bit of product rule on this to get, I guess, a minus sine x by differentiating that one, leave that one alone, and then leave that one alone, differentiate that one. And I get a bit more product rule here, and it's also a bit of implicit differentiation as well. Y squared differentiates to 2y times dy by dx because you're differentiating with respect to x. So that's all of this stuff, and then you leave this one alone. And then you do the other half of product rule, leave that one alone, and differentiate this one, and then just differentiate sine x. So we get all of this, but we can actually then put in the fact that we know at this point, we're still talking about this point, we still know dy by dx is 0, so this term's going to go away. We now know that this term here, d2y by dx squared, is minus 1, so that can go in there. And we still know this stuff from up here, so we can put all of that in, and we end up with, after you do a bit of cancelling out and a bit of timesing by root 2, you end up with what was required, which was nice. So we end up with this here. And now it says determine the Taylor series for this. So we follow the formula, the formula up here. So we've got f of x is equal to f of a. Now a is pi over 4. Now, so f of pi over 4, well, that's just 1 by definition. They gave us that right at the start. That's what this point means. X minus pi over 4 into f dashed at pi over 4. Well, that's the first derivative at pi over 4. But we worked that out, right? Well, it's a stationary point. We didn't. It's a stationary point. So that's 0. The first derivative at this point is a stationary point. Therefore, it's equal to 0. d2y by dx squared, we did work out. That was minus 1, if you remember. So that goes into this point of the formula, and then we just copy this stuff out. And then the last term was this, as they said here. So that goes in there, and then we end up just with this bit here. And we can simplify that up, and we end up with something that looks a bit like that. And moving on, we have Leibniz's formula. So call that one f of x and call that one g of x. This is just how I like to do it. Differentiate this one 4 times to get all of this. Pretty straightforward. Differentiate this one. Ooh, hang on. I've got this wrong. I should have used... No, I haven't. I'm just an idiot. Okay, differentiate this one 4 times and you get all this. I thought I'd messed this up because I couldn't remember doing this step properly, but I have done it properly, that's fine. And d4y by dx, the 4, is equal to this one times this one, plus 4 lots of this one times this one, plus 6 lots of this one times this one, 4 lots of this, and then just this and this at the end. It's just a binomial expansion. So the coefficients come from the binomial expansion of, to the power 4, which is 1, 4, 6, 4, 1. And then you just combine these two, you combine these two, you combine these two, you combine those two, and those two finally at the end. And then if you just combine everything together by just grouping the sines and the causes, you end up with what was required. And then funny here, a bit of just regular A-level maths to do. We know we can factorize out the 3x from this guy here, and then we just need to make this thing look like r sine x plus alpha. So just expand out x sine of x plus alpha using the sine compound angle formula. It makes this, and now we need 28 sine x to be equal to r cos alpha sine x. So therefore r cos alpha is 28, and likewise r sine alpha is this 96. Just comparing the coefficients of cos. Divide this by this, you get tan alpha as this, and then you find alpha as this, and then you can use this one to find r, and you get r as this thing here. You could have also used Pythagoras to find r. And that goes in there, and you get this here. You can factorize it out, the r out again, and you get this. I assume they were just 3 marks short on this paper, so they thought, let's throw in some A-level maths. Why not? You do have to know it all. Okay, these are the bits from the formula book that we need for ellipses and hyperbolas, so I've got those bits next to each other. The eccentricity of h, which is given by, h is a hyperbola, so it's given by this thing here, is the reciprocal of the one for e, which is this one here. So okay, in this, let's start with the ellipse. Clearly a is 5 to make 5 squared 25, and b is 3. So let's put that into this formula here and work out e. You get 9 over 25 is 1 minus, so that's going to be 16 over 25 is e squared, so e is 4/5. E has to be a positive number, so no need to mess around with the minus there. And the eccentricity of h is the reciprocal of that. So therefore we flip that over and we get... I shouldn't have put a minus here. It's not the negative reciprocal, it's just the reciprocal. I don't think that's going to make a difference, because when you square it, it goes away anyway. Cool. So this should not be a minus. I was thinking gradients and negative reciprocals. My mind instantly typed the negative. I don't need a negative here, but it's not going to matter, because when you put in e squared over here to find a and b, of course this squares to 25 over 16 anyway. That's why I didn't notice the mistake until now, is because it doesn't make a difference. I also don't even think I'd lose a mark for this, because you don't even get a mark for writing this down. You get a mark for the answers, I guess. I'm not sure. Anyway, e squared is this. So let's just write an equation in terms of B and A here. And then, of course, we can use the second idea to find another equation in B and A, which we'll then use to solve for B and A. So the foci here is given by plus minus AE. But we know A is 4/5, and we know A is just 5. Well, 5 times 4/5 is 4. So that's just plus minus 4, 0. And that's the same as the foci for the hyperbola. Now, we know that the hyperbola has, again, this should be not a minus, but again, it doesn't make a difference because you can be plus minus anyway. So when you times them together, it doesn't make a difference. Plus minus 5/5 A has got to be plus 4 minus 4 because the two foci are the same. This just comes from my incorrect E dash, but it's fine. It's not going to make a difference. Times by 4 divided by 5, you get A is this, and then shove that result into there. You can do it without a calculator if you want, because all the stuff just cancels, and then you can root this for a 4 and a 3 and a 5, and it just becomes 12 over 5. And those would be the two answers. Apologies for the mistake there. That shouldn't be a minus, nor should that. None of it makes a difference. The same two answers apply at the end. I'm going to use some T-substitution here, or some Weierstrass substitution. So firstly, dt is equal to a half sec squared theta over 2, d theta, just differentiating this. Now, sec squared is the same as 1 plus tan squared, and tan squared is just t squared, which is really useful. So you can say this is 1 plus t squared and divide, and you always end up with this result. You don't even need to derive it. If you've done enough t formulas, you can just throw this down on the page, and you don't need to derive it here. Just write it straight down if you want. Likewise, you can write sine theta as this and cos theta as this. You don't want to derive these. These take too long to derive. You don't want to waste your time doing that. Just write these two results down and just shove them straight in. There will be good YouTube videos on somewhere deriving these. Please watch them if you want to. But that's not the point of this video. You shove those results in. You write this as 2 into 1 plus t squared over 1 plus t squared, and then combine this entire denominator together to make this. Now you can cancel this 1 plus t squared with this one. That's why this substitution works so well in any integral that looks a bit like this, is because of that cancelling right there. And because this is just a quadratic on the bottom, which we can complete the square on, which is what it's asking us to do. And the reason that's useful is because, of course, you have a formula for doing this, for doing integrals of the form x squared minus something else squared. So, okay, we got to there, that's fine. And now I'm going to say, well, if theta is 2 pi over 3, t is tan of 2 pi over 3 over 2, which is 2 pi over 6. And you can type that into calculator, or just know tan pi over 3 is root 3. And then you can do the same with pi over 4, you get 1. And now, of course, you can put those there. You didn't have to do that, right? You could have just integrated this and then put the theta back in, I guess, and then put these numbers in, but it's up to you. Anyway, the integral of this form is given by this, again, from the formula book. So we're just going to write that down, right? Our a is just 1 because 1 squared is 1. And we can just say x is t plus 2 because it's a linear transformation. It's not going to make any difference to the derivative. So we can just say that x is t plus 2 here. And you can put those numbers in. And yeah, this is log of a half here when we put that in. The 2 cancels with the half out here, which is nice. This is log of a half. Take away log of half is the same thing as dividing by a half inside the log. But that's just timesing by 2. So that makes this. And then we just need a new page and we need to rationalize this. And then we times this out. And it ends up being this, which cancels some more. And you end up with this here, which is what they asked us to do. Got another question here about ellipses and parabolas and stuff. So first thing, it's asking us about the tangent. So we should just look at this and we should just differentiate it. We get 2y dy by dx equals 4a. Of course, we can divide by 2a there to get this. And now put that y in here, 2at, but that's just 1 over t when that stuff cancels there. So the gradient is 1 over t. We can now bust out y minus y1 equals mx minus x1 because we know y1 and x1 and we know the gradient. So that goes in there, and this just rearranges nicely to the thing they wanted you to get. So that's good. I kind of messed this rest of this question up because I should have just used this immediately, but I essentially just decided to go back to the start. I don't know why. I put this x and this y into here to work out that a must be 2 because you end up with 8 and 16 over here, so a must be 2 to make that work. The k squareds cancel. And then I just went from the top. I don't know, I'm just an idiot. I went from the top and just said, well, if a is 2, you can differentiate this and get this. And then you can do the whole thing we just did again to get dy by dx is this. Now put in the y coordinate for b, and you get the derivative is 4 over 4k, which is 1 over k. And for c, it's minus 1 over k because it's just a minus there. And now do y minus y1 equals mx minus x1 from them separately. Again, I'm just an idiot. You could have just used all the work that you did in the first part, but who cares? And now, of course, if we want, so this is the tangent at b, this is the tangent at c. If we want those two things to intersect, we just need to find the intersection point. So let's just take this y value, add 4k to both sides, I guess, and just, or in fact, no, I think I took this one. I took away 4k from both sides here and then just threw the whole result into there, which gives me this. So take away 4k, that gives you essentially this part of it, which is y. Put that in there, and then minus 4k, the rest of it's the same. Times by k and rearrange some stuff, you eventually end up with this. And then, of course, if x is minus 2k, you can put that back in this line. Sorry, where am I putting that back in? I've got x as this. So yeah, that's the intersection of this tangent and this tangent. So of course, if you put this x coordinate into this tangent, you'll find the y coordinate, which is the same as which is where the intersection will be. But of course, when you do that, you get minus 2k minus another 2k squared is minus 4k squared. Divided by k is minus 4k. So you get y minus 4k equals minus 4k. So y is therefore 0, which is very helpful because when you draw that on a graph, that means d is over here somewhere. Minus 2k squared is 0. And then b and c are like up here and down here somewhere. So this is a triangle that's entirely symmetrical with a height of 4k squared and a base, I guess we can think of it as 8k. So therefore, a half times 4k squared times 8k is this number here, and then we just times by 2 and do some stuff. And you end up with k is 3. That isn't the whole question, because if k is 3, you then need to work out where a and b are, but of course that's quite trivial. You'll get b and c. You'll get b and c as that, and you'll be done. Question 9 is the vectors question. The intersect, well, if we just crowd these vectors up like this, we need the x coordinates to be equal and the y coordinates to be equal. We can solve that. We can also solve simultaneous equations. Just do it. You get this. We should probably, although it's completely implied, let's just check that the z coordinates also intersect at this point. And 1 minus 3 is minus 2, and 8 plus 5 lots of minus 2 is minus 2 as well. So that totally checks out. So that's fine. So this is the intersection. Just doing that to make sure you haven't made a mistake on the simultaneous equation is probably worth your time. But anyway, once you have these, you can put these back into either one of these 2 points. It doesn't matter. And you get the coordinate as this here. Plane contains both the lines. Find an equation for it. So Cartesian equation has the coefficients being a normal vector to the plane. To find a normal vector to the plane, you cross multiply the two vectors that are within the plane. So these two vectors here. So let's just cross multiply those two things. I do it like this. If you do it a different way, that's fine. But for me, it's just I lots of this times this minus this times this, which is 22. Sorry, no, it's not, because this makes it positive, and then you take it away. And then it's minus this into this times this minus this times this, which makes that, and so on. So that's the normal vector. And so now you can just say it's 18x minus 16y minus 10z equals k. But now you know 2 points that lie in this plane. We only need one of them. Put this point in it to find out k. And we'll get k as this, and so that will be our plane there. The last question is also kind of interesting here, because it's actually just A-level maths again. We've got two lines that pass through 0, 0, 0. So in vector form, the lines need to be looking a bit like this. That's a line they pass through, and then it's plus some amount of a vector that we'll determine in a second. So in Cartesian form, it's going to be x minus this over this, plus y minus this over this, plus z minus this over this. Sorry, equals in between, not plus. And you get this. So it's x minus this over a equals y minus this over b, and so on. So we're looking for something that looks a bit like this, I guess, in the end. Now, how do we get the a, b, and the c? Well, making an angle with 60 from the x-axis, from regular A-level maths, you have that cos alpha, if you make an angle with the x-axis, cos of that angle is x over the modulus of the vector that you're looking for, the length of the vector that you're thinking about. Now, we're thinking about this vector here, ABC. So let's just say the vector is this. That means that cos of 60, if we're making an angle with the x-axis, cos of 60 is our x1, which is a in our case, over the length of this vector. So we end up with something that looks a bit like this. Now, cos 60 is just a half, so that's nice. This bit's annoying, but we could just pretend that this vector is length 1. The reason we can do that is because we can make this vector kind of bigger or smaller just by having different values of k, which aren't going to matter to the end answer, right? K is not part of that. So let's just make this vector length 1, which will make root a squared plus b squared plus c squared 1, which is great, because then we just get a half equals a. And likewise for the next one, we have cos 45 is b over the length, but again, we're just pretending the length is 1. So that makes 1 over root 2 is b. But now we have a and b, we can actually make c such that the vector makes the length 1 that we were looking for the whole time. So we can say a half squared plus 1 over root 2 squared plus c squared must equal 1 based on the maths I've already done. So c squared, that makes a quarter, that's a half. So 1 minus a half minus a quarter is a quarter, so we get that, and then we root it to get plus or minus half, which is where the two lines are going to come from, because now we can just write this out. X divided by a half is 2x, y divided by this is root 2y, and z divided by this is plus or minus 2z. So those would be our two lines there that we need to use. Funny that they use this in this paper. Kind of interesting, kind of nice. Anyway, question number 10 is the differential equations question. We've got this substitution here, so let's differentiate it. Dx by dt, t differentiates to 1. Leave this alone. Small product rule here. Leave t alone, and then u differentiates to du by dt. Differentiate this again. d2x by dt squared equals du by dt, so that's this one differentiated. And then product rule here. So differentiate that for a 1, leave this alone, and then leave this alone and differentiate that for this. So that's the two results here. Let's throw those two results into here. We end up with this. I don't think I've made a mistake there. I'm just going to expand everything very slowly. Expand, expand, expand. Just hope that stuff cancels. A couple of things do. Not a lot though, but a couple of things do. So we can cancel those out and we can end up with this. And now these things look close. Of course, notice this doesn't have any t's in it, aside from the derived by t bits. So let's think about getting rid of these t's, or think about getting rid of these x's, because this definitely doesn't have any x's in it. So, okay, well, of course, all right, firstly, I divided by t cubed, because I also noticed that this doesn't have any t cubes anywhere. This needs to have a coefficient of 1, so divide by t cubed. And now I think what I'm going to say is, well, x is just ut, so put those in, and then when you cancel these t's, it turns out that this term cancels with this one. And when you cancel those t's, again, that term cancels with that one, and you just end up with what they were requiring you to get, which is excellent. And so we're done with those 4 marks. And then finally, given p is at O, so that means x is 0, its displacement is 0. But if x is 0, u is 0, right? Because 0 equals, yeah, sure, so that's fine. So now we can solve this. Now this is of the form m squared minus 2m plus 0. So let's just solve the auxiliary equation. We get m is either 0 or 2. So our first bit of the solution is a e to the 0t plus b e to the 2t. And now let's set u to be maybe k e to the t. Differentiate. Differentiate again. It's very interesting. Put these results into here to find k, which will be minus 8, I believe. So our full solution looks a bit like this. And now we know u equals 0 when t equals log 3 and when it equals log 5. So put in log 3 and put in u as 0, and then put in log 5, put in 0. This 2 has to go here before you can cancel the in the log, so this makes e to the log 9. This cancels straight away just to make 3 times 8 is 24. But now this cancels to make 9b. Move the 24 over there. Do the same stuff over here. And now take these away and divide by 16, and you end up with b is 1. Which therefore then will get ua is 15. So we can put those results back into here, and we get this. And yeah, it says to the solution to I though, not to this. It says to I. So now we just need to replace u with x over t again, times by everything by t, and that will be the answer to that question. Thank you so much for watching, and I'll see you next time.